Thank you to the organizers. I don't know whose idea it was to put me at the step. I was worried she'd be a tough act to follow. I never expected it. Not to say. But she did it, but actually it's good because she's presented something in a much better way than I would have. So some of what she said. I do have a nice memory of one of the first times that I met Richard. And here it is.
I know.
It's not moving.
It's bad.
Turn it on.
Yeah.
There it is. Okay, this was the seminar.
Adriana.
The summer seminar. You see, what was that? So there's Adriano,
Use the SD Cabrionics. That's cute.
Richard Stanley, Dennis Stanton, Jeff Remmel. I'm not sure who the woman is.
Who the woman is. Ah.
So Steph already talked about the Stanley's chromatic symmetric function. So here's, you don't have to spend much time on the slide.
Yes.
Colors are numbers.
Get out of it.
So that's why there are numbers for red. 7 is for red, 23 is for blue, and so on. It doesn't matter. We'll need these numbers in a minute. Oh, and by the way, and when you replace the first m variables with ones, you get the chromatic polynomial. So that's why it's called chromatic symmetric function. Symmetric, and it reduces to the chromatic polynomial. And I first heard Richard speak about this in Taormina, where Sarah Billy showed that beautiful picture of the beach in Taormina at the conference. So that was the first time I heard that chromatic symmetric functions. Okay, so the famous Stanley-Stembridge positivity conjecture, there it is. If it's the incomparability of a 3 + 1 coset, then it's E positive. And here's an example for the paths. A coefficients are all positive. And Gacharoff gave
Yeah, you can AI.
the sure basis,
Generate.
showed that it's a sure positive. K showed that the Stanley-Stembridge conjecture is equivalent to this. Just needed to be a unit,
You know this stuff.
which is a subclass of this. So if it's a unit interval graph, then it's E positive. That's the conjecture. So Shureshian and I came up with a refinement of the chromatic symmetric function. We call it chromatic quasi-symmetric function. We introduced this parameter T. T is counting the number of descents in the coloring. So that's why these numbers matter. Colors have to have an order for this to make sense. And the descent is a pair, like 1, 4, that edge, where the color is bigger, color of 1 is bigger than the color of this node. So 1 is less than 4, but its color is bigger than the color of 4. And we call that a descent. And so we put this additional parameter in. With this additional parameter, we can look at the coefficients. We can view this as a polynomial of T and look at its coefficients. Those are not necessarily symmetric functions, but they are quasi-symmetric functions.
He speaks clearly.
So the question is, when are they? When are those coefficients symmetric functions? Well, we show that if it's a natural unit interval graph, so that's a unit interval graph that has a very natural labeling to go with it, because by labeling, I mean the numbers that we labeled and those.
Correct.
So the natural unit interval graph, then the coefficients of t are all symmetric functions. That
Okay.
was,
If you ever see her, let me know.
so we'll focus on the symmetric functions that are chromatic quasars. So our refinement of the Stanley's temperature conjecture is that if you have a natural unit interval graph, then the coefficients are positive and also be unimodal. So here's an example for the past. And here are the coefficients. They are palindromic also, 4. And you can see that this example, the coefficients are E positive, and by E unimodal, that just means when you subtract this from this, you get a D positive symmetric function. You go up to the middle, and it's always difference is always D positive. So that's what E unimodal is. Qureshi and I were able to modify Gacharov's result and show that this is always Schur positive. So we can expand it into Schur functions, and we were able to get the coefficients also. So we showed that it's Schur positive, but we couldn't get Schur unimodal, just as Schur positivity. So we wanted to get Schur unimodal, of course, and so we thought that a way to do it would be to use the Hard-Lefschetz theorem, to find some variety with a group action, a symmetric group action, and that the cohomology, when we apply the Hard-Lefschetz theorem, we'll see the unimodality, and the Frobenius characteristic will be this. So that was our goal, and so we were looking around for varieties. I was picking up a homework assignment that I was teaching out of EC1 and making up a homework assignment for my class. And I found an exercise of Richard's that said to prove that a certain generalized Eulerian polynomial was unimodal. It was an Eulerian polynomial, but it was a generalized one. And I said, wow, that's a specialization of the result we're looking for. So I had to do it, of course. I looked at the solutions, and in the solution, it said Hessenberg variety, which I didn't know anything about. So that was the clue. So now we had to look for an action of the symmetric group on the Hessenberg variety. And find one. And so the next thing we found out, we learned later, that Julia Tamaccio had representation not on the Hessenberg variety, but on the cohomology of the Hessenberg variety, that the symmetric group representation of the cohomology. And that's exactly what we needed. And so we tested this out, and that's what I just said. And we came up with this conjecture that when you apply omega, plus percentage constant, that this is the Frobenius characteristic of the J cohomology, 2J cohomology, Hessenberg variety, and this is a sequence of numbers that corresponds to the graph. Actually, I'm not giving details here, but the point is we found our representation cohomology. And this, from the Hard-Lefschetz theorem, this tells us that this gave us the Schur unimodality about the conjecturally gave us the Schur unimodality that we wanted here. Sure. So this is true Schur unimodality.
Sure, you fidelity applies to the standard.
It's weak. So, no, yes. So, so I presented this conjecture 10 years ago at the Stanley at 70 conference celebration. And it turned out, so Timothy Chow was in the audience and he got interested in the conjecture and he enlisted the help of Patrick Brosnan, and together they proved that was exciting. And thank you for your 70th birthday. And so, and you can see from this, it was not easy. And then Dave Paquet came up with another proof of the conjecture. Oops. That was very different than about compound. So there were now two proofs of this conjecture. So that's the second conjecture is true. But the first conjecture, positivity, is still open.
What you're saying is the 90th birthday.
You already knew it for the empty graph and the complete graph, it was easy. We proved it for the path, actually, we knew it for the path before we even started this, and that's what led us to this whole business here. Recent times, so this was before 70, Stanley at 70, but in recent times, there's been further developments on various infinite classes of graphs.
Oh.
And we, on the computer, we verified it up to n. Here's the thing, there's been a lot of activity on studying these chromatic fluidity positivity or related results for these chromatic quasi-symmetric functions. This is a sample. I've been very nervous that I'm leaving out important results here, but let me know afterwards if I left out something you think should have been in this list. There's lots of things that should be in this list. But here's a sample of other developments that happened after the conference. Not immediately, throughout the years. Okay, so that is all I'm going to say right now, or all I'm going to say about the Stanley's chromatic symmetry, quasi-symmetric refinements. And I'm going to now move on to a different generalization of the chromatic polynomial. So we leave it stand. So here's the non-Stanley chromatic symmetric function. It's based on this Whitney formula for the chromatic polynomial. And we're taking the Mobius function for the bond lattice of the graph, and this is the number of blocks in the element bond lattice. The bond lattice is a subset of the partition lattice. In red is showing for this graph. In red, these are the showing what elements are in the bond lattice. Okay, and in the bond lattice, notice we don't have 1 and 4. We don't have 1, 4. That's not included because if the induced subgraph of 1, 4 is not connected. The induced subgraph has to be connected in order for us to have the block in there. So that's the bond lattice. So what I did with my former student, Rafael Gonzalez de Leon, is we looked at a weighted version of the bond lattice. And what we did is we attached weights to each element, each block actually, of each element of the bond lattice. So this is the graph, this is its bond lattice, and each block got weights attached. So we attach any composition, in ours too, we want to attach a weak composition of the size of the block minus 1, and the length is r. So in this case, the length is 2, and so this is a composition of 2, 0 plus 1. It's a composition of, let's look here. So this is a composition of the block size minus 1. Block size is 3. This is a composition of 2. This is a composition of 1 minus the block size, 2, 1 minus is 1. So we attach weights that to each block. I didn't say what the order relation is. It's a natural relation. I don't really want to spend the time on what the order relation is. So we get this weighted bond tocent. And one other thing is the weight of an element of this weighted bond set like this is what we do is we add the two compositions component-wise, and then we add 1. So if I add, no, we don't add 1. We have to go up. I'm sorry, we just add the weights. So the weight of this element is 0, 1. Not a good example. We add the weights. And we first got interested in this because when G is the complete graph, this is related to the Freely algebra with R compatible, R different kinds of brackets, but they're compatible. So this is like what Phil was talking about on Tuesday, relationship between the Freely algebra and the partition lattice. But if we weight the partitions in the partition lattice, then we get a relationship between that and the Freely algebra with R compatible brackets. So that's why we started looking at this, but then we looked at it for graphs as well. So that's it. And then we define a polynomial. So we have a graph, and we have an R, a positive integer, and we're going to polynomial x1 to xr by taking the Mobius function in this coset and over each element, and we are now looking at x1 to the weight of the weighted partition, x through xr to the weight of the x. So we get this monomial times the Mobius function, just like in Witten's. So we take this path graph. This is the weighted bond lattice, the path graph, and here we look at this. This is just contributing 1. That's the monomial. This is contributing. We add these together, so we have 0, 1, and it's now contributing x2, x1 to the 0, x2 to the 1. So we get x2. And this is also contributing. Weight is the same as this one, so it's contributing another x2. And so these two come from these two. I'm sorry. This comes from these two, this comes from these two, and then the rest, the degree 2 terms, come from the top ones.
Det är den som jag tar.
So we get this inhomogeneous symmetric function. I put it in terms of the e's. And here we have negative, but degree 0 is positive, degree 2 is positive, degree 1 is negative. So we're going to call this alternating E positive. And then we turn this into a symmetric function. We were looking at symmetric polynomials. We turn it into a symmetric function by allowing compositions of infinite length. And this symmetric function has the properties that it's symmetric. And it has the stabilization property. And it reduces to the chromatic color when we put zeros and reverse. And this is just the coefficients of this is just the reverse of the coefficients of chromatic color. So now if we restrict to the degree D component, we and take the path, the graph is the path, we show that this is equal to Markman's parking symmetric, parking function symmetric function. Yes. And oh, I thought we were leaving Stanley. I guess that's just impossible in this. So, because the parts, Richard showed that the parking function, symmetric function, can be decomposed this way in terms of the complete homogeneous symmetric functions, where this is a set of non-crossing functions. So, pretty result. And that implies that when we multiply our top degree, this actually the top degree. This is the top degree, and n-1, when we multiply, we get this. Okay. This is okay. So we get it in terms of the dimension. So the top degree piece of this symmetric function multiplied by sine is E positive. And so we're going to say this is alternating positive. So for the path, it follows from Richard's result that it's alternating positive. Here's an example again. And we proved that if G is a chordal graph, then it's alternating E positive. And we gave this decomposition of the elementary functions with the top degree. This. And so this reduces to Richard's result when we did okay, which is a chordal graph. Certain set of trees instead of take the place of the non-clustering functions. And we use Richard's R labeling technique to compute Mobius function, and that's what gives us this result. But actually, we're not sure that it doesn't hold for all graphs. It might hold for all graphs, but our technique doesn't work on all graphs. But it could be true that we verified it for n less than or equal to 7, which is probably pretty small. But it might hold for all graphs, and it's all. And there's another specialization that's interesting. Before we specialize by letting that be some value, and this be old called lambda, I guess we're calling it T now, and this is 0. Now we're making this 1 and looking at the highest degree component of this symmetric function. When we have the path, it's a Narayana type. When we have the star graph, it's a binomial Eulerian polynomial. And both of these polynomials arose in the work of Kosmakov, Reiner, and Williams, where they showed that these polynomials are the H polynomials. This one, well, this is what's known. This was already known. This one is the H polynomial of the isosahedron, which is the same as the graph isosahedron of the path. This one is the H polynomial of the graph association of the star graph. Of the graph association is the stellar cube. So that this coincidence, this H polynomial, caused me to conjecture that it's always going to be true whenever the graph is a tree, that you're always going to get the H polynomial of the associated graph association. And it turned out, okay, it was proved by Gonzalo, very recently by Gonzalo de Leon, Avila, Korea. G is a tree, then this specialization is equal to the H polynomial of graph association. So it's an interesting connection. They have more general results also. What about log concavity? We don't have to worry about that alternating property because now everything, we can ask about log concavity. We'll say it's sure log concave. This is true. This is sure positive. Take the degree D squared, take the degree D minus 1 and D plus 1. This might be a far-fetched conjecture. We haven't really worked on it or tested it, but it seems nice. It would be nice to work. And sure, let's see what, make sure we see what that means. So let's recall that this is when we have the path. We have this as our chromatic vector function. And we can check that the Sherlock concavity condition, we square this and we subtract off this times this, we get that. That's not E positive, but it is sure positive. Not a lot of evidence. We check this up to n equals 7, but maybe that's small. So log concavity would imply log concavity of specialization. And that would imply this famous conjecture of Reed is a famous proof of Geological. So I don't know if that makes this even more far-fetched, or maybe the proof that he used can be pushed through this. But this is more general. And I see this for true. Okay, and speaking of June, I want to excerpt from Geological's citation for the ICM of June Fields Medal, 2022 Fields Medal, and this is what it says. Guess we only care about item 2 right now. And so it says his went on, of course. So the result I had on the chromatic polynomial is amazing that it took so long to prove it was unimodal, but a lot of time came applied to unimodal, but it's a hard problem. And that was part of the citation, that work. But then he went on to do other amazing work. Collaborators, and that was also part of the citation, so that Karen wrote a Welsh conjecture. And this is, so Richard played a big role. So just wanted to point that out, and also I wanted to congratulate Richard on getting the Steele Prize 2 years ago. a one-time achievement. Thank you.
Questions?
Hi, Michelle, thanks for the talk. I was wondering, if you could go back a slide, when you talk about, yeah, when you talk about using the Juneho's results to try and push that back and improve log concavity, have you looked at this recent sort of stuff with these Lorentzian polynomials, which is sort of more clearly algebraic?
I haven't really spent time on this, but this might be, I don't know if they do show positivity results.